Define a function f on the positive integers as follows. F of n equals m, where m is the least positive integer such that n is a factor of m squared. Find the smallest integer m such that the square root of m is both a product of at least 3 distinct prime numbers and a factor of the sum of f of d, where d is the divisor of m. So let's take a long hard look at this problem because it is very, very confusing at first. So let's try to get a feel of what f does, and then we'll move on to this scary looking sum, which I'll actually call like g of m or something like that. So we can reference this big sum as needed. But what does f do? F takes a number n to another number such that n is a factor of the square of this number. And let's try out some simple cases. F of 1, well, what's the least positive integer such that 1 is a factor of the square of that integer? Well, 1 is a factor of the perfect square 1, which is the smallest perfect square. So f of 1 equals 1. And in all of this, we can actually be thinking a little bit about like how, which perfect squares that this number stacks up against, and then actually taking the square root. So what's the smallest perfect square that has a factor of 2? Well, it is 4. 4 is the smallest positive perfect square that has 2 as a factor, and the square root of 4 is 2. So f of 2 equals 2. F of 3, well, smallest perfect square with a factor of 3, 9. Square root of 9 is 3, so f of 3 is equal to 3. F of 4, what's the smallest perfect square that has 4 as a factor? Well, 4 is the smallest perfect square that has 4 as a factor. It's 2 squared. Since 4 is 2 squared, f of 4 is equal to 2. And similarly, you can go on and keep adding some stuff. But why don't we try a few more examples with a little more complicated numbers? How about f of 8? 8 is 2 cubed. What's the smallest perfect square that has 8 as a factor? Well, it's 16, and 16 is 4 squared, so f of 8 is equal to 4. Now let's keep trying powers of 2 because this actually looks pretty interesting. F of 16, well, what's the smallest perfect square that has 16 as a factor? It's 16, and 16 is 4 squared, so f of 16 is 4. F of 32 is equal to 6, no, not 64, square root of 64, which is 8. Because 64 is the smallest perfect square with a factor of 32 in it. And f of 64 is also 8. And you can sort of say that f of like 2 to the power of k is equal to another power of 2, and in fact it's equal to the power of floor of k over, no, ceiling of k over 2, excuse me. Ceiling of k over 2. Like, for example, f of 2 to the power of 4 is 2 to the power of ceiling of 4 over 2, that's 2 to the power of 2. F of 2 to the power of 5 is ceiling of 5 over 2, which is 2 to the power of 3, which is indeed 8. Huh, interesting. F of 2 to the power of k is 2 to the power of ceiling k over 2. What if I do that with powers of 3? I will get the exact same thing. And in fact, if we take any prime p and take f of p to the k, we get p to the ceiling k over 2. But what if the number has more than one prime in its prime factorization? What if I have a number like 2 to the power of 3, 3 to the power of 2? What do I do here? Well, basically what we're doing is we're looking for a perfect square that has this guy as its factor. And in fact, the smallest perfect square is 2 to the power of 4, 3 squared. And we take the square root of that. So f of 2 to the power of 3, 3 to the power of 2 is equal to 2 squared times 3, which is 12. And more or less in general, you actually have f of p1 to the e1, p2 to the e2, where the p's are primes and the e's are exponents, all the way up to like pk to the ek. This is equal to, well, the first thing we do is we find a perfect square that has this guy as a factor. And the way we do that is we look at e1, and if it's even, we just say, okay, p1 to the e1. And if it's odd, we say, well, you bump it up by 1. So like, for example, 2 cubed will become 2 to the power of 4 for the perfect square of the prime factorization. And then in the end, you would square root it. So each prime acts completely independently of the other in some way, shape, or form. You end up with p1 to the ceiling of e1 over 2, p2 to the ceiling of e2 over 2, pk to the ceiling of ek over k. And once again, you can sort of try to convince yourself that this would actually work. That the best way to find a f of a number is just bump up each of the exponents if they're odd to an even number. And since the perfect square has all even exponents in its prime factorization, you can just take the square root. So this is a little bit how the function f works. Now, how does the function g work? Well, you basically take the sum of all possible factors, and you take f of each of them. And for now, why don't we just completely disregard all of the constraints that square root of m is both a product of at least 3 distinct prime numbers. And m doesn't have to be a factor of g of m right now. We're just going to get a feel for what g of m actually does. And what we will see is that g of m works sort of like finding the sum of all divisors. Like, remember when you found the sum of all divisors of the number 72. Like 72 is 2 cubed times 3 squared. And then we claimed that the sum of all factors of this was 1 plus 2 squared plus 2 cubed, 1 plus 3 squared. And the reason is because if you try to expand this out without taking the sums first, you get something like 1 times 1 plus 1 times 2 plus dot dot dot, where every term just conveniently happens to be a factor of 72, and every factor of 72 is only hit once. And what this g is going to do is something extremely similar, because let's look at g of, for example, 36, which is equal to 2 squared times 3 squared to get a better feel of this. Okay. Well, we actually have to find the sum of 9 factors of 36, the f value of those, right? So you have to find f of 1, 2, 4, 3, 6, 12, 9, 18, and 36. And I wrote it this way for a specific reason. And the reason is because you can look at f of 1, f of 2, and f of 4, and you can say, well, f of 1 is just 1, f of 2 is 4, and f of 2 is 2, excuse me, and f of 4 is 2 as well. We already specified that. So f of 1 is equal to 1, f of 2 is equal to 2, f of 4 is equal to 2. Now, what's f of 3? F of 3 we found was 9. And you can look at f of 6 and think, well, f of 6, that's just 2 to the 1 times 3 to the 1. So f of 6 should be 6 as well. And excuse me, f of 3 was actually 3, my apologies. F of 12, what was f of 12? F of 12 was also 6. And that's because you take your primes are 2 squared and 3, and you run them through this, and 2 becomes 1, and 1 becomes 1. And so f of 12 is equal to 6 as well. And you can look at 9. F of 9 is 3, f of 18 is 6, f of 36 is 6. And you can verify them for yourself if you don't quite believe me. And look at what we do here. We, instead of any of these 9 terms, we write something like this: 1 plus 2 plus 2 times 1 plus 3 plus 3. And the reason why we do this is because we notice that each of these 3 columns is sort of a multiple of each other. Each of the rows is sort of a multiple of each other. And when you expand this all out, you will conveniently get each of these 9 terms, right? So, in essence, g of 36 is equal to this stuff, which is equal to 5 times 7, which is 35. And if you were to continue trying g with some other bigger numbers, you're going to end up with, like, for example, g of 2 to the power of 5, 3 squared, 5 to the 6. I'm making this number off the top of my head. And you're going to get something like 1 plus 2 plus 2 plus 2 squared plus 2 squared plus 2 cubed times 1 plus 3 plus 3 times 1 plus 5 plus 5 plus 5 squared plus 5 squared plus 5 cubed plus 5 cubed. And the reason why is because when you expand all these out, every one of these guys is going to conveniently be f of one of the factors of these guys. And you can sort of look at this, just the factor including the powers of 2, and it will have 6 terms. And if you were to take, for example, the third term, this is akin to f of 2 squared. This guy is f of 2 cubed. This guy is f of 2 to the power of 4. This guy's f of 2 to the power of 5. And you can see that you can sort of tack on more and more primes and more powers. And this whole thing is still going to hold. If this doesn't convince you, try it out for yourself with some other numbers. In general, what we're going to get is, let me clear out some space, that g of p1 to the e1, p2 to the e2, pk to the ek is equal to, well, we look at the first prime and we talk about, well, the sum of f of p1 squared, etc., etc. But really, g of p1 to the e1 is equal to 1 plus p1 plus p1 plus plus p1 to the power of ceiling e1 over 2, where this top number is repeated one time if the exponent is even. And so you can sort of do the same thing for each of these primes, where you take the sum from exponent equal to 0 all the way up to the exponent be equal to e1 over 2 ceiling, or no, excuse me, just the sum up to e1, and you take p1 to the power of ceiling e1 over 2, right? And then you do the same thing with p2, p3, p4, p5, and then you just keep taking these products, I equals 0 up to e2 of p1 to the power of ceiling e2 over 2, so on and so forth. You do this for each of the primes, and we multiply them all together. Okay, if that wasn't helpful because it seems too technical with too much notation, why don't we just get down to our meat and potatoes of how we would actually look at what this m is, such that square root of m is both a product of at least 3 distinct prime numbers and a factor of g of m. So m is a factor of g of m, and has the square root of m is a product of at least 3 distinct prime numbers. What does that imply? M is a perfect square, right? Because if m is not a perfect square, square root of m is not even an integer, so it wouldn't make sense for it to be a product of prime numbers. So let me clear out most of the stuff here, and maybe just leave the G definition stuff. All right. So what this guy really tells us is that we can treat each of the primes separately, right? Because if you look at this entire product, the sum for P1, the sum for P2, this guy is just equal to G of P1 to the E1. This guy is just equal to G of P2 to the E2, and so on and so forth. So the product of all of this is equal to G of P1 to the E1, G of P2 to the E2, G of PK to the EK. Now, what is M? M is a product of, square root of M is a product of at least 3 distinct prime numbers. So we can say M is equal to, I don't want to overuse P, so Q q1 to some exponent a1, q2 to the a2, dot, dot, dot. But all these powers have to be even numbers because m is a perfect square, so let me just drop a 2 here, and then qk to the 2ak. And note that there have to be at least 3 primes, and preferably we want exactly 3 primes because the more primes in the prime factorization, the bigger the number will be. All right, but this thing sort of implies that we can treat each prime separately. So why don't I just look at some of the smaller primes, because smaller primes are very interesting. And why don't we start by looking at the prime 2 and finding g of 2, g of 4, etc., etc. So g of 1 is equal to 1, g of 2 is equal to 1 plus 2, which is 3. G of 2 squared is 5. G of 2 cubed is 9. We had 4. G of 2 to the power of 4 is 13, and so on and so forth, with g of 2 to the power of 5 being like 21 or something or the other. We could keep going, we don't need to. Let's look at the prime 3 as well. G of 1 is equal to 1. G of 3 is equal to 4. And the whole reason we're doing this is because we can just take any of these guys, and multiply them together. And because g is closed under multiplication, this is just going to work if we just look at each prime individually. G of 3 cubed is 16. G of 3 to the power 4 is 25, so on and so forth. All right. Now let's see. So let's look at 5. G of 1 is equal to 1. G of 5 is equal to 6. G of 5 squared equals 11, so on and so forth. I'm just going to do this for the primes 5 and 7 because we'll actually sort of need them. G of 5 to the power of 4, excuse me, this should be 11 plus 25, which is 36. This guy should be 61. Finally, we look at the prime 7, where g of 1 is equal to 1. G of 7 is equal to 8. G of 7 squared equals to 15. G of 7 cubed is equal to 64. G of 7 to the power of 4 is equal to 113. All right. Now notice, m is a perfect square. So we only care about even numbered exponents. All right. So we can sort of erase all the unnumbered exponents because they don't pertain to our problem. Because m is a perfect square, m's not going to have 2 cubed as the power of 2 in its prime factorization. That's just not going to happen. Okay, my claim is that m is odd. So we seem to be running out of space already here. Claim m is odd. The reason is, let's say that m is even. Okay? And actually, I might get rid of this stuff so we have more space. Let's say that m is even. Then what we say from m is that, well, m is a factor of g of m. However, g of m is just a product of g of, like, for example, g of p1 to the e1, g of p2 to the e2, so on and so forth, where m is equal to p1, e1, p2, e2, stuff like that, right? However, if you take a look at these guys, all of them are odd. And with some experimentation, you can find out that that is indeed true. The reason being, when you go from something like 5 to the power 4, 5 to the power 5, and 5 to the power 6, g of 5 to the power 5, and g of 5 to the power 6, all you're doing is adding on one more factor to the number within g. So you're just adding on one more f. But this adding on from 5 to the power 4 to 5 to the power 5 is going to be the exact same thing as you're adding on from 5 to the power 5 to 5 to the power 6. So you're adding the same thing twice to an odd number, so you're going to get another odd number when you get to 5 to the power 6. And that is always going to be the case, which means that every single one of these guys is odd. If m is even, m cannot be a factor of an odd number. That means we can already disregard 2 as a factor of m. So we don't have to worry about this, okay? So m just has to be a product of odd numbers. It's got to be a perfect square, etc., etc. All right, and now what do we do here? We might be stuck. Why don't we try a small case? M has at least 3 distinct prime numbers. M is a factor of g of m. There doesn't seem to be any other way to do this after eliminating even numbers. So why don't we just try a test case, the smallest possible case, which is m with 3 factors, 3 distinct prime factors, 3 times 5 times 7, but m is a perfect square, so we give squares to all of these guys. We try this, just the small, this is the smallest possible remaining value for m, and it turns out it works. And you can look at this just by looking at the table. G of m is going to be equal to g of 3 squared times g of 5 squared equals g of 3 squared times g of 5 squared times g of 7 squared. G of 3 squared is 7. G of 5 squared is 11. G of 7 squared is 15. Square root of m is 3 times 5 times 7. This is a factor of 7 times 11 times 15. So square root of m is a factor of this guy. M is a product of at least 3 distinct prime numbers. This guy actually works. You can't get any smaller than it, but it works. So therefore, this is our answer. And if we look at this, we get that it's 105 squared, which is 11,025. And this is our answer. After a lot of hard work, we have found our answer, and we are done. Thanks for watching, and I will see you next time.